from this model ends up with the B0 plus the B1 term. Female non-smoker just ends up with the B0 term. We again subtract the bottom equation from the top. We get the conclusion that in this model, B1 represents the log odds of disease for non-smoking males to non-smoking females. The effect of male sex only among the non-smokers. If you were a 2-pack-a-day smoker, you want to talk about 2-pack-a-day smoking men versus 2-pack-a-day smoking males to see the effect of males among 2-pack-a-day smokers, well, plug in 1 for male, plug in 0 for male for the male and the female. Plug in 2 for packs. The male has a value of 1 times 2 for his value for male packs, the female is 0 times 2. That means the male gets a value of B0 plus B1 plus 2B2 plus 2B3. But the female just gets the B0 plus the 2B2 from this model. Subtract the bottom equation from the top, and we see the effect of male versus females among 2-pack-a-day smokers is not B1, but it's B1 plus 2 times B3. So if B3 were non-zero, this model is going to tell us that the effect of male versus female depends what type of smoker you're talking about. If you're talking about males, females who are non-smokers, that's what the B1 term means. But if you're talking about 2-pack-a-day smokers, not just B1, it's B1 plus 2 times B3. So when we look at this model, this coefficient of male, 0.524, just notice it's different from what we had before. The odds ratio is no longer 1.97 or 1.98, it's 1.69. Because this number 1.69 compares males to females who are non-smokers. If you want to compare males to females who are 1-pack-a-day smokers, you have to take the B1 term and add a B2 to it. If you want to add a B3 to it. If you want to talk about males and females who are 2-pack-a-day smokers, it's a B12 term plus 2 times the B3 term, as we saw in the previous slide. So the interaction term in the model means that the effect of male no longer means what it was before. It no longer means the effect of males versus females regardless of your smoking level. It only means the effect of males versus females among the non-smokers. So the interpretation changes when you have these interaction terms in the model. And more often than not, you would like to be able to get by without having interaction terms in it, because then you have an easier time interpreting the coefficients of the other factors in the model. But including interaction terms essentially allows for the existence of effect modification. And fortunately, in this case, there's not a significant relationship between the male tax variable and your outcome. There's the evidence in this data supports the null hypothesis. So in this case, I would probably go with the previous model. So that's what I wanted to say about model assumptions and how to choose one model versus another, models that make different assumptions. Let me talk a little bit before we conclude this exercise in logistic regression, talking a little bit about precision of these odds ratios. If I go back to the previous slides, let's suppose I go back to the model that had male and packs in it. Remember, the estimate of the smoking adjusted effect of male versus females is an odds ratio of 1.98. It gave me a confidence interval that went from 1.48 to 2.67. Where did this confidence interval come from? It gave me a p-value for the significance of the effect of male versus female controlling for smoking. The p-value was less than 0.0001. Where did it come from? It came from this chi-squared test, 21. Where did the 21 come from? It came from dividing the coefficient by its standard error. So let's talk a little bit about standard errors. And because they impact the size of this p-value, they also impact the size of this confidence interval. Because, what slide was I on? The next one. The confidence interval came from taking the coefficient of male and adding and subtracting that 1.96 times its standard error. So let's remember what standard errors mean. The printout gives you a value for the standard error for the male coefficient, 0.1477. Conceptually, what does that number mean? Conceptually, it means doing the following. We did one analysis here with 1,363 people in the Framingham Heart Study. Imagine doing many analyses on different people. Imagine having many, many different data sets. all of which have 1,363 people, the same type of people we have in this data set, but they're different people. In each of these other data sets, I'm going to fit a model that has male and Paxton. I'm going to fit the same model to these different data sets. Well, if they're the same type of people, the coefficient of male is going to change a little bit from model to model. It might be 0.68 in one analysis. It might be 0.67 in another analysis, 0.70 in another analysis. Let's imagine each of these analyses being based on 1,363 people, the same types of people that I have in my one single data set. Let's imagine I keep track of all these different coefficients of male. My one analysis gave me a coefficient of 0.6838. But I have many, many analyses now. I've filled up a blackboard with different values for the coefficient of male from these different analyses. And now I ask, what's the standard deviation of all those numbers? That's what the standard error is estimating. Estimated standard deviation of your sampling distribution values. Sampling distribution means repeat the analyses on similar people, each time calculating the same value, the B1 term. So if the standard error is small, that means if I looked at that blackboard full of numbers, those numbers would have a small standard deviation. Those numbers would be very similar to one another. Meaning one study is just as good as any other one study. It's a very precise result. Result doesn't change from study to study. But if the standard error was big, that means, yeah, my results change. They're not very precise. One study could give me a different result from another study. Well, the standard error is therefore measuring the precision of the results from your one study. Whether they're precisely estimating a result, meaning whether they give you results that are similar to what results you get from other studies built on similar people. Well, what impacts, now let's go back to what impacts the value of the size of the standard error? And the biggest thing that impacts the size of the standard error is your sample size. Later on this month, we'll be fitting models in SAS, if you have SAS on your PC. If I asked you to make a mistake intentionally, read your data set into your workspace twice. So you don't have a data set of 1,363 people. You got a data set of 2,700 people. You got twice the size data set. You fit that model to that big data set with twice as many people, each person being counted twice. You're going to get the same value for B1. You're going to get the same value for B0. You're going to get the same value for B2, for your fitted coefficients in that model. But what is going to change is your standard error. It's going to become smaller. As you might expect, bigger data sets are going to give you more precise results. They're going to give you results which have standard errors which are smaller. So one thing that impacts the size of the standard error is the sample size. Standard errors will decrease with increasing sample size. But when you're fitting models, two other things impact the size of your standard error. The other things depend on what else is in the model. It turns out, in the model I just looked at, we had male and we had smoking in the model, male and PAX. We've been looking at the standard error for the B1 term. How does PAX impact on that? It turns out that the other factor or factors that you put in the model predict the outcome. In other words, they're strong risk factors. Your standard error for your coefficient of male is going to actually decrease. So you improve your precision by including in your model other risk factors that impact a person's risk of getting heart disease. That's good news, meaning a model is going to become more precise if you include the other risk factors, the other reasons why people get heart disease, as other predictors in this model. But there's a downside to that too. If those other risk factors are related to your single risk factor of interest, you're focusing on the coefficient of male. If those other risk factors are related to a person's gender, like smoking, males might smoke more than females, then it turns out that the standard error will increase as those other risk factors predict your exposure of interest, your male. And that's what we mean by collinearity. To show you, or multi-collinearity, if you're talking about multiple risk factors. Before I show you an example, let's just think about confounders. Confounders are other risk factors that have two properties that we talked about. They are risk factors for developing the outcome. In the previous bullet, that means including confounders in a model is going to help me because confounders are risk factors for the outcome. They're going to predict the outcome, so by including those confounders, my standard error might become smaller. But remember, confounders